Today I want to talk about our topic, a distributed KV database based on ROT. The basic problem of distributed KV database is how to store data on a single machine and how to ensure the availability and consistency of the whole distributed system. The reason our project is called Senate KV is because we believe it is like the Senate of ancient Rome, where leaders are democratically elected and then make a series of efficient decisions. We have conducted some research for this purpose. We have many options on how to store data on a single machine. When we researched our service, we found an interesting storage engine based on LSM tree. LSM trees means log-structured merge tree. Its most famous implementation in industry is LevelDB. We studied LevelDB, which accelerates writes using log appending, and the accelerates reads with multiple levels of redundant data compression and indexing methods, such as filters, and uses write-ahead log to guarantee crash recovery after a crash, and all data is persisted. I think the advantage of this storage engine fit well with the usage scenario of distributed KV database, so I choose it. As for how to ensure the consistency and availability of the distributed system as much as possible, since the logs on multiple machines must be at least linearly consistent, we need distributed consensus algorithms. We conducted research and found ROT to be a distributed consensus algorithm that is easy to understand and not difficult to implement. So we choose it. During our design and implementation, we encountered some challenges, mainly focusing on 3 areas: fault tolerance, consistency, and scalability. Fault tolerance is the key to ensure high availability of distributed system. When a node fails, the data being processed by that node and not synchronized to other nodes will be lost. And if this problem occurs in multiple nodes at the same time, then even consistency cannot be guaranteed. The linear timeline of the whole system is disturbed. Even without node failures, consistency problems remain because the network is not as reliable as inter-process communication on a single machine, and no I/O-intensive software uses synchronous I/O these days. Network unreliability is further amplified in asynchronous I/O scenarios. So the synchronization of data between multiple nodes also faces a challenge, both in terms of linear consistency. And the normal nodes need to be aware of crash nodes so that they can make adjustments to the overall system state change. We can guarantee read consistency, by which I mean, of course, linear consistency. For example, a read after a write, will definitely not read a version of the data that is earlier than the previous write by itself. In addition to data itself, the states of the nodes need to pass to each other. So replication of the logs is also necessary. And another important role of logging is to ensure the atomic nature of commits. For example, if a commit is not successful, then the data should be returned to whichever version it was before the commit instead of some intermediate state. For distributed KV system, the main application scenario is a large number of fast writes as well as a small number of reads. So the strong consistency is a more appropriate consistency model with a small number of reads. Strong consistency can guarantee availability as much as possible. Since we choose election first and the leaders later, approach as the most basic architecture of our distributed system, the conflict problem will only this in the brain fracture problem. That is, the whole system is divided into two regions because of the poor network condition. This means that the whole system is divided into two regions because of the poor network condition, and then different leaders and decisions emerge. For this problem, we insist on setting the number of nodes in the system to an odd number, so that unless the number of the nodes in odd isolated partition is not in the majority, which will not guarantee availability, then availability is guaranteed to the greatest extent possible, because then there will always be a majority group. Their leaders have absolute decision-making power. But if we introduce the function of node change, then brain fracture and then brain fracture will not be the problem. The node change issue is more complex. Single node change at the time is really relatively simple, but less efficient. A single change that allows multiple nodes will require at least two forces to reach final conformance, which can be a legacy process. This is very much like the grayscale release of a new version of a business system that goes to live in an internet company. When the volume of the data increases, adding nodes is a wonderful solution. However, the locks in the origin nodes become very bloated and redundant due to their special way of writing, appending. So it is crucial to compress the logs. The most intuitive way to handle this is to update the oldest version of the current nodes log to the latest version that has been synchronized by most nodes. For a failed node, we prefer to assume that it failed due to a recoverable error at a software level. So we insist that it be rebooted rather than replace it with a new node. Because a good database system does not write the configuration into the code, but reads the relevant configuration from the configuration file. This is a better way because hot plugging is more convenient. That is also beneficial for node changes. Let's go into my raft.go file. The first I want to talk about is a request vote RPC. This is a request vote RPC. Request vote RPC function is a handler of voting request. It will be executed by the nodes, which is requested by the nodes which are re-electing. First, we have to lock the mutex of the route object and defer unlock to the end to the function. If the term of requester is smaller than the term of a voter, the voter will reject to vote. And if bigger, the voter will turn to follower state. And if the voter has voted for the candidate in the previous election, it will check the last logs terms and indexes. If the requests are newer, the voter will vote for it. Finally, the voter will persist its states asynchronously. And then let's go to append entries RPC. This is append entries RPC a little bit long. Append entries RPC function is a handler of synchronizing logs from the leader to the followers. It is executed by receivers. First, we have to lock the mutex of the route object and defer unlocking to the end of the function. If the leader's term, as you can see, if the leader's term is bigger than the followers, the receivers will keep or become the follower. If smaller, the receivers will end this handler. If the leader's logs are newer than receiver's log, the receiver will replicate the new logs from the leader, and then the receiver will adjust states of their own and do the shrink for the logs. Yeah, this is a shrink. As you can see, the delete log entries, this is a shrink process. It will discard the logs which has been replicated by most nodes. Finally, the voter will persist its states asynchronously. Let's go to the leader election function. This is the leader election function. In leader election function, a node that has become a candidate because it has not gotten a follower of the leader's heartbeat for too long, will start the election. It will call request vote and RPC to request votes asynchronously from all other nodes, and then get the results in the origin routine through the channel and count them. If the number of votes is more than half, the election is successful. If some newer nodes are found, it will turn itself into follower. So as you can see, it will turn itself to follower. And this means it can be the leader. And the main logic for route instance is in each node is in make route function. A loop, each round is checked for timeouts. As you can see, this timeout, and this is loop, and asynchronously executed. And this ensures that our election can start. Now let's go into the mykv server.go file. This is the only function I want to talk about, the operator handler. The operator handler function will asynchronously be called in *kv server function by each node. It executes a loop for handle all operations from the client. It receives commands from a channel. This is channel from a channel and do the relative operations to the storage engine. That's it.
Okay, here's my let me make a demo of our project. First, here is our configuration file of our project. So each server has a configuration file, and in these files it contain all the server's IP address and port. And here is the client configuration file because it's easy to know all the servers in the cluster. And now let's run our cluster. First, we need to run all the servers. Okay. We got five nodes in our cluster. Now also are running. We got 5 server, and then we can get our client run. Then we have 4 command can be used here. First is get, put, and append, and finally is exit. At first we can put a king A and value is B in the KV store, and then we can get A, and also we can append a value after B. So I can get A again. You can see 3B here, and finally, if we don't, if we want exit, just tap exit here, and we can exit this paragraph. This is all the function here. We got and when actually we use level DB, so the data is persisted here. And if we let's check which is the leader here. The load 1 is we can see it's leader here, and just we going to crash it, and it will begin a new leader selection, and we can now here load 5 is a new leader, and he try to collect load 1 all the time. So this is a problem we need to solve because it's not hot plugging, and then but it's not influence our function. We can also use function here. We can get a now is you can see that we can get a successfully, right? And we can start this server again. It will copy all the dates command we run before, and this is an important step of the consistency. Okay, so in our cluster there is at least three loads. That is to say, we can tolerate two load value. So this is for tolerance. Okay, this is all the function I would like to show. So that's it, and please Henry to continue his presentation.
Okay. So